Welcome to This Explainer. If you're tuning in, you probably already know how to hack together a basic script and get your code to run. But today, we're shifting gears. We're moving away from just achieving basic functionality, and we're stepping right into the realm of true computer science. We're going to master memory-efficient, highly scalable architecture by leveraging Python's built-in functions. And to be clear, these aren't just simple wrappers for basic tasks. They are highly optimized, C-level implementations designed to absolutely supercharge your code. All right, let's look at our roadmap for today. We'll be hitting 5 key areas: leveling up your Python, building efficient data pipelines, synchronizing data streams, critical system diagnostics, and finally, inspecting unknown data payloads. Let's jump right in. Section 1, leveling up your Python, from syntax to scalability. The traditional beginner approach usually leans heavily on writing explicit for loops, right? You end up juggling state variables, writing a ton of boilerplate code, and honestly chewing up a dangerous amount of system memory as your datasets grow. It just weighs everything down. But advanced Python, it's a whole different ballgame. It leans into functional paradigms. By ditching those line-by-line manual loops, you instantly shrink the surface area for logic bugs. And even better, you massively reduce your memory footprint using techniques like lazy evaluation and O of 1 space complexity.
Section 2, building efficient data pipelines, the power of map function and filter function.
So imagine you're running a weather satellite station, or maybe managing a massive global array of IoT sensors. Suddenly, boom, you receive 10 million temperature readings in Fahrenheit, and your backend system needs every single one of those converted to Celsius for standard storage. If you try to run a standard for loop to build a brand new list with those converted values, well, generating that massive object all at once is going to instantly eat up a huge chunk of RAM. You'd likely bottleneck the server, or even worse, crash the whole process completely. Enter the map function. It's an absolute lifesaver here. Map is what we call a higher-order function, meaning it actually takes another function as an argument. But the real magic? That's lazy evaluation. Instead of hoarding memory by transforming all 10 million items up front, it just hands you back a super lightweight iterator. It just sits there in your system, taking up practically zero space, maintaining that sweet O of 1 space complexity. And it only does the mathematical transformation at the exact microsecond your program asks for the next value. It literally gives your system room to breathe. Okay, so we can transform data efficiently, but what about cleaning it? Picture an e-commerce platform right in the middle of a massive Black Friday rush. You've got millions of users writing reviews, but mixed into that fire hose of traffic are spam bots, malicious URLs, and completely empty data blocks. If your machine learning backend tries to chew through all that garbage data, your queues are going to back up, and those servers will absolutely buckle under the computational load. This is where the filter function absolutely shines. Think of it as an elite, ruthless gatekeeper that uses a predicate function. Now, a predicate function is beautifully simple. It just looks at an input and spits out a strict true or false, nothing else. So as this massive stream of data pours in, filter acts like an instant data sieve. If the predicate says true, the data passes through cleanly. If it's false, dropped, instantly. And because filter also uses lazy evaluation, it cleans house without ever building a giant secondary filtered list in your system memory.
Moving on to Section 3, synchronizing data streams, the zip function.
Let's pivot a bit to another huge backend headache, making sure data across multiple streams lines up flawlessly. Think about the live logistics backend of a ride-sharing app. You might have one server tracking a list of available driver names, another one tracking live GPS coordinates, and a third holding fleet IDs. To show a user their driver's profile, you have to sync all 3 of those streams in real time, purely by position. If you try to manually juggle the indices using a basic range loop, you are asking for an index error. I mean, what if the GPS list updates faster than the names list, and your loop calls an index that just isn't there yet? The whole function breaks. Python solves this beautifully with zip. Honestly, just picture a mechanical zipper on a jacket. Zip takes elements from matching indices across all those different collections and just securely locks them together into a unified tuple. And here's the best part. If those lists happen to be uneven because of some network delay, zip cleanly and automatically stops exactly at the end of the shortest list. It completely shields your program from out-of-bounds memory pointer crashes, and you don't have to write a single line of custom length checking logic. Section 4, critical system diagnostics, global invariant checking with all and any. Now we're getting into critical operations engineering. We're talking about environments where failure is simply not an option. Imagine you're writing the autopilot software for a passenger jet. Before takeoff, hundreds of diagnostic flags absolutely must return true.
One single false reading, say fuel pressure drops slightly, and that sequence has to abort instantly. Or think about a cybersecurity network. If even one defensive node out of thousands spots a breach, the alarm needs to go off immediately. You definitely do not want to be writing clunky, deeply nested conditional statements for life or death checks like that. Instead, we bring in all and any. Both of these functions rely on a highly aggressive optimization technique known as short-circuit evaluation. With the all function, it scans sequentially, but the exact microsecond it hits a false, it stops completely. Mathematically, the overall condition is already broken, so it instantly abandons the rest of the checks, saving critical processing time and triggering the abort. The any function does the exact same thing, but in reverse. It shorts out and sounds the alarm the very moment it detects a single true condition. All right, our final module. Section 5. Inspecting unknown data payloads, dynamic interrogation with type, dir, and evaluate. In modern software engineering, you're almost never working in an isolated silo. You're constantly pulling in data from massive open source frameworks or, slightly messy third-party APIs. So when a totally unrecognized payload hits your system at runtime, how does your code actually know what it is? Is it a standard list, a dictionary, some highly customized class object? And crucially, what actions can your code safely perform on it without throwing a catastrophic error? We handle this gracefully using a dynamic introspection pipeline. Step 1, we scan it with type, which basically acts like an identity badge scanner, telling us exactly what class blueprint built the object. Step 2, we hand it over to dir, which maps out a full detailed directory of every single attribute and method packed inside. And step 3, we can even filter out those internal double_dunder methods to isolate just the exposed public operational capabilities. Basically, your system can dynamically double-check exactly what a foreign object can do before it even attempts to interact with it. Now, as you dive into dynamic evaluation, you're inevitably going to bump into eval. It is undeniably powerful. It takes raw text, parses it, and runs those dynamic strings as actual living Python expressions at runtime. But please heed this massive security warning. Never, absolutely never, use eval on untrusted user input. Because it executes strings exactly as if they were native code, exposing it to the outside world is basically leaving your front door wide open for massive arbitrary code execution vulnerabilities. Hackers could easily pass in strings that wipe your databases or completely compromise your servers. To lock all of this in, we've got a quick reference table summarizing the explainer. Notice how everything we've talked about aligns with real-world impact through their time complexities. Map and filter operate lazily in O of n time, letting you chew through massive arrays without getting stuck in nested loops. Zip runs optimally at O of the minimum of n and m, perfectly and safely merging parallel data. And all provides your global invariant checking with a max of O of n, but in reality it's often way less thanks to the processing time saved by short-circuiting. And that brings us to the ultimate question. We've moved way beyond just getting a beginner script to run. Now that you actually understand how lazy evaluation, short-circuiting, and O of one memory footprints work under the hood, how are you going to architect your next codebase differently? It is time to boldly strip out those clunky boilerplate loops, embrace these highly optimized functional paradigms, and build something genuinely scalable.